So, good morning, everyone. We can start the next session. Thank you. My name is Ziye, and today my colleague Changpeng Liu here and I will talk about the SPDK vhost, a practical solution to accelerate storage IOs inside VMs. Actually, in this presentation, we will talk three kinds of SPDK vhost solution. They are SPDK vhost-scsi, block, and NVMe, and we will talk about their implementation and performance. So this is today's agenda. We will have a brief introduction, and mainly we will pay attention on the vhost NVMe implementation in SPDK. And then we will have some performance comparisons among several kinds of implementations. And finally, we will talk about some future work, such as maybe some patch work in QEMU or others. So this page just let's review the vhost idea to accelerate the virtio. We know the idea is very clear. The vhost idea is we have a separate process for the I/O processing, and we use the vhost protocol to communicating the guest parameters between QEMU and the separate process, and we can negotiate the such information of the virtio protocol. For example, the memory, the number of virtio queues, or the virtio queue locations, and definitely we can have the vhost kernel target solution, or also the user space solution. And in this, in our topic, we will talk about the user space implementation. So this page is just the SPDK introduction. I will not tell the information here, but the emphasis is that since we build a SPDK-based user space vhost target solution, and our purpose is to use limited CPU cores to maximize the IOs for different VMs. It means that our goal is to use vhost target to serve so many virtual machines with good performance, but with limited CPU resources, or the CPU resources you can control. And let's review the SPDK's vhost target architecture to accelerate the virtio-scsi or block. We just use the vhost protocol, and we leverage DPDK's IT vhost library and transfer the request from SCSI or block protocol to SPDK's BDEV layer. And finally, we can pass these IOs to real NVMe devices, or emulated devices, or self RBD devices, or third-party devices, which implements the SPDK BDEV's semantics. So the question is that will SPDK vhost only for SCSI block be enough? I think the question here is not. Since currently we have the NVMe protocol, it defines the parallel and high-performance interface, which is designed for the non-volatile memory backend, especially actually the PCIe SSDs. And this is a trend. Actually, it can have multiple submission queues and completion queues, and all these submission completion queues can be used to submit IOs concurrently. So compared with the SCSI protocol, definitely the NVMe protocol is much more lightweighted. So it can finally decrease the latency for each IO submission and also the completion. Thus, in the guest virtual machines, from the OS side, we can see two different of controllers. If you use the virtio-scsi block, the guest OS see these controllers. And if you use the NVMe driver, actually you can see the NVMe controllers. And definitely, we hope to provide a transparent solution to the guest VMs. It means that the guest VMs can still use the native kernel NVMe driver, and it can see the NVMe controller. This is our goal. And so we provide the SPDK vhost NVMe solution. Actually, from this diagram, you can see that we compared 8 kinds of different solutions to accelerate different accelerate the 3 different protocols in the guest VM. They are the virtio-scsi, virtio-blk, and the NVMe interface. And from the left side, it's all the software solution. And in the right side, there are 4. They are hardware-based assisted solution. We just compare the guest OS interface, backend device sharing, and the live migration support, and the QEMU support, and finally the NVMe hardware are required. And in this diagram, the star means the features can be either supported or it depends on its own implementation. So we can see that I think the most important, 2 important things is about the first is the backend device sharing. Whether we can share, if there is only one NVMe SSD, whether we can share the devices among the VM. And the second is the live migration support. So we can see that with the red color, the M in the column means that it is not supported. But there is still M in SPDK vhost NVMe. Since currently the QEMU support is not merged, it means that. But we already have patches, and we would like to discuss with community guys like Red Hat and others, and to negotiate a possible solution to make the SPDK vhost NVMe acceleration solutions can be acceptable by users. So why we need SPDK's solution? Since there are still some issues related with the hardware. The first issue is related with the naming space. If you are familiar with the NVMe protocol, you can see that if you use the IOQs to submit a request, you need to identify the naming space ID. But if currently the hardware solution, it can use the splicing IOQs to provide the IOQs to be shared among the VMs. However, the naming space ID isolation or virtualization, it is still not solved. It means that every virtual machine should see its own naming space. For each VM, maybe the naming space, it also starts from 0, 1, 2, 3. But if you use a hardware solution, you cannot achieve that. And the second is about live migration support. Currently, there is no mature method to tracking the dirty IOs or pages if you use the hardware solution. Either you can just, I think, during migration, you can migrate the hardware state to the software state and just use the emulation, software emulation methods to do the IOs during migration. But it will, the performance will be decreased. So I think there is still issues related with hardware. And the third, it is related about some advanced features such as quality of service. Currently, SPDK's purely software solution can be fine-grained to achieve this purpose. Thus, the quality of the services among VMs on the same NVMe SSDs, the QoS can be guaranteed. But for the other solutions, it is still not consider such a situation, but they may consider it later. So with this, we combine the we can compare the SPDK's previous SCSI block solutions with the vhost NVMe solution. Actually, we reuse something. For the vhost protocol, the initial usage is only for accelerating the virtio, but we can extend the vhost protocol to support the NVMe virtualization inside the guest OS. And the second is that we can see that in the left diagram, for the virtio vhost acceleration, we share the virtio queues. And the difference is that for the NVMe virtualization, we share the NVMe's submission queues and the completion queues. So it is slightly different. So next part will be the implementation details. It is time for my colleague, Changpeng. Thank you.
Okay, I will go through the implementation details. So this diagram shows that SPDK use target can support both the, both the three interfaces. The first one is virtio-scsi, and the second one is the virtio-blk, and the third one is the NVMe controller. You can just start one SPDK slave target and to support those different interfaces. And for the QEMU part, you can use inbox QEMU driver for the vhost-user and the vhost-blk. And but for the NVMe part, we maintain a separate patch in our own GitHub repository, and you can apply that patch and test over this. For the slave target part, we have three different components. And below that components, we have our block device layer, which can be used for the physical NVMe device and the AIO device and the self-RBD, etc. So as you may know, the vhost-user solution is basically the core idea is that to share the different IOQs between the guest and the slave target. Here, the socket message is used to set up such communication channel. And for the NVMe solution, we reused a lot of existing vhost code to set up the communication channel between the guest and the slave target. The first one is set event notifier. It's used to check the asynchronous event report feature in the backend slave target. And the second one is set guest notifier. This message is used to set the completion queues RIQFD inside the guest. And the most important one, I think, is the set memory tuple. Is used to set the shared memory between the QEMU and the slave target, so that the SPDK slave target can convert the IOs sent from the guest to implement the zero-copied IO offload. And we added two extra socket message to implement the NVMe protocol. The first one is the admin pass-through command. So this command is used for the slave pass in the NVMe spec. And we embedded some mandatory admin commands in this admin pass-through socket message and to implement the software solution. The other ones we call the set or get controller configuration. It's used to kick and start the NVMe device and disable this NVMe device. So this is for the existing implementation. For the future plan, I think it's not quite accurate to add the two vhost messages into the existing vhost library. It may not make sense. So in future, we may drop the two messages based on different implementation. So for this one, I already just said, for the set memory table used to map the shared memory between the QEMU and the guest and the set notifier, we can reuse the existing vhost message set variant call to set up the IOQ. And for the other part, the third one is set get config. It can be used to get the PCI bus basis registers. So one proposal from us is to extend the existing QEMU vhost library and make it can be used for the non-volatile devices such as NVMe. Maybe we can rename the vhost user library. Maybe we can rename it to PCI user. Maybe it will make more sense. So this is the example to show how we can set up the shared IOQs between the guest and the slave target. So the guest will send the create our submission queue command first. And this is the spec definition for the create IOQ. And the PRP is a pointer to point to the submission queue's physical address inside the guest. And when submit to the admin queue, and it will write the PCI register as a doorbell. And the QEMU will capture this admin command and send this command via the vhost domain socket to the slave target. And then SB will got this command and make memory translation. Here the memory translation is from GPA to HV, gets the physical memory address to host the virtual address. So after this step, both SPDK and the QEMU can see the same submission queue now. So this is the same for the completion queue. So let's see one data path optimization for the IO command submission. So NVMe 1.3 introduced a new feature we call shadow doorbell buffer config. With this feature, when submitting the command from the guest will not write the shadow doorbell. Will not write the PCI registers. It will write into the shadow doorbell instead of the PCI registers. This feature is enabled from Linux 4.12. So some new Linux kernel will already enable this feature by default. From the SP side, we can both support the shadow doorbell buffer and the traditional older Linux kernels. We can pull the shadow doorbell buffer and the PCI bar 0 doorbell registers at the same time. Depends on the user's choice. So of course, performance is improved when the shadow doorbell is enabled. So this is the shows how this feature work. So submit a new I/O and write to the submission queue once doorbell. And if this runs in the guest OS, it will cause the VM exit, right? And so with this new feature, it will write to the shadow doorbell. So after this enabled, so NVMe protocol becomes a great parallelized protocol. So this is one example for the I/O execution process. Guest will send this new I/O to the submission queue, and the SP will start a poller, just polling this submission queue, and it will pick up this new request and send to the backend devices. And after the backend completed this I/O, it will post the completion entry into the completion queue, and will inject the IOQ into the guest. Here there is maybe there is one thing for here for the completion path. They will have a user to kernel context switch for the IOQ injection, and at last the kernel guest will get this response and finish this I/O. So for next, we will see some performance benchmarks. This is one example. We just start one VM with one NVMe SSDs. The purpose is to want to get the KVM events to evaluate the efficiency for this new solution. The yellow one is QEMU NVMe solution. It's in-box QEMU solution. And the other three parts are vhost-user solutions. You can see that for the vhost-user solutions, the IOPS is very high. We use the one NVMe physical controller. The hardware limitation for this controller is about 550 IOPS for random read IOPS. You can see that for the vhost NVMe solution, it can almost hit the hardware limitation. And we can also see for the CPU utilization level, we can see that we can see not too much different from the vhost NVMe to compare with vhost-blk and SCSI solution. And the other one is we started 8 VMs with 4 NVMe SSDs. This is kind of some common use scenarios. Users may want to share one NVMe SSD with different VMs. So this is another test scenario. So we can see for the vhost NVMe solution, it will get better for the IOPS, and for the latency part, we'll have lower latency. So one question here is, because Linux NVMe driver will pull completion queue while submitting a new request to the submission queue. So with this optimization, which can help to decrease some interrupt numbers, and will help with some, the latency part. Because from the implementation view, vhost NVMe and vhost-blk should have at the same levels performance number. They will have too much difference, just because the NVMe spec is more common compared with virtio-blk. Virtio-blk is so simple that it can only support read-write, the simple commands. So it's a summary. So for this solution, native NVMe driver can be used inside the guest, and we do not need the actual parallel virtualized driver. And for the IO submission paths, we do not have VM exit. And we do have IOQ completion when we inject the IOQ to the guest VM. There's a user to kernel context switching. And all the vhost-user solutions are zero-copied for our commands. And for this solution, it can also benefit from Linux block driver, which enable the multi-queue features. And compared with virtio-scsi protocol, NVMe spec has fixed 60 bytes for commands and 16 bytes for the response. When users submit our vectors and commands, it is more efficient compared with virtio-scsi protocol. And of course, for existing vhost-user solution, for the purpose to implement zero copy, a whole table is required to use this solution. And some future work, the first one is that we already said that for the hardware assistance solutions, migration is hard to add. So this is 100% software solution. So for the migration part, we can add to this feature support very easily. And the next part, maybe we want to upstreaming such an idea to the QEMU GitHub repository, and to make more users can benefit from such solution. And the third one is in future, we want to add container support for this idea. Okay, Q&A.
Oh, hello. On the back.
Hi.
Thanks for the presentation. I think this shows how promising the results are in terms of using a single process that can pull everywhere, and the results speak for themselves. I wanted to ask a question around the choice to use vhost for the offloading process. As it would appear that vhost is more meant for the I/O-based devices. And I was wondering if you could comment on the choice of using vhost versus perhaps proposing a virtio NVMe protocol, where NVMe commands can be passed over virtio and then vhost just naturally works. Or maybe trying to use something like a VFIO, perhaps with MDEV or something else for that purpose.
I think both those ideas can work, but we definitely need to figure out one solution that can get better CPU utilization and get better outputs with the lower CPU utilization. So pooling is a great idea compared with some other solutions. And emDev solution I already mentioned in the Ziye already mentioned in previous slides. For the scalable IOV and emDev ME, for the NVMe interface, they will require a lot of code. And the scalable IOV definitely cannot work with NVMe device because the namespace issue. You must figure out the namespace issue to use scalable IOV. And for the emDev part, you must implement a totally emulated NVMe device in the kernel side to benefit from hardware solutions. So we evaluated all the different solutions, and we still think this kind of idea is not too bad.
Yeah. How do you think migration will work with SPDK? Do you think you'll be able to use any of the existing block migration schemes?
No. So for the migration part, we can only support to migrate another, maybe another server. We can just make it can work. And for the block migration, it cannot support it because we do not have a US-based file system, and we cannot track which block is used and which block is empty.
Okay, so we are out of the time, so if you have any questions, you can discuss it during the break, so thanks.
Thank you.